Hi everyone, this is Mrs. GA, and today we are going to be proving figures are congruent using rigid motions. So we're going to start with a little bit of vocabulary. So first, congruent. The definition of congruent is exactly the same shape and size. So if two figures are exactly the same shape and size, we can call them congruent. And then here we have the definition of polygon. So a polygon is a closed plane figure formed by three or more segments such that each segment intersects exactly two other segments only at their endpoints. And we'll interpret what this means in just a moment. And no two segments with a common endpoint are collinear. So what it essentially means is that first you have to have three or more sides, and each side, both endpoints match up with another endpoint from a different segment. So pretty much it's saying you can't have something like this, because here you can see this endpoint doesn't match up, this doesn't, this doesn't, this doesn't. So it needs to be a closed figure where all of the endpoints meet up with another endpoint. Here we have a three-sided polygon, which we call a triangle. A four-sided polygon is called a quadrilateral. Five-sided is pentagon. Six-sided is hexagon, and eight-sided is octagon. Okay, so now we're going to talk about the more formal definition of congruence. So we can say that two plane figures are congruent. And just so you know, the symbol for congruent looks like this. So it's like an equal sign with a little squiggly on top. We're going to use this for congruent. If and only if one can be obtained from the other by a sequence of rigid motions. So just a reminder, the three rigid motions or rigid transformations that we know would be translations, so shifts, reflection, or a rotation. So these are the type of transformations that maintain the size and shape of your figure, meaning that they are maintaining congruence. So essentially, if we can show that we can map one figure onto another using one or more of these type of transformations, we can show that they're congruent. So here we're going to be using the definition of congruence to decide whether or not they are congruent. And we're going to explain our answer with coordinate notation for transformations. So here we have two quadrilaterals, and it looks like that this one is congruent to this one. So let's see if we can prove it. So it looks to me like there's a horizontal and a vertical translation going on. So let's see if it's consistent for all of the points. So from A to E, I can see that I go right 3, down 4. So that works. For B to F, I go right 3, down 4. For D to H, I go right 3, down 4. And then C to G, right 3, down 4. So since it's the same movement for all 4 points, we can write this rule. We can say X, Y becomes X plus 3, right 3, and Y minus 4. So this shows that we can map one onto the other using a translation. So now, since this is shown, we can prove that they're congruent. Now here's the thing, you do need to make sure you match the corresponding points from the figures. So if I'm going to call that first figure A, B, C, D, and I'm going to say it's congruent to something, I need to make sure that this A value matches with this value right here, which is E. I need to make sure that if I write A first, I'm going to write E first here. And since I have B next, the corresponding point is F. C corresponds with G, and D corresponds with H. So you have to match the first coordinate with your image coordinate using this transformation. So this is a valid statement of congruence. Now let's look at this next one. So you can see in this figure, it looks again like they're congruent, so we have to show it using a rule. So it looks like this line would match up with this line, here would match with here. You might even see like this looks like it should match with this. So if you can find parts that look like they should match up, that may help to determine your transformation. So here, it looks like we should have a reflection over the line y equals x. Now we can confirm this by checking our coordinates. So let's compare L, M, J, K with the coordinates of Q, R, N, P. So let's take a moment and find those coordinates. Okay, so you can see here I listed out the coordinates, and if you compare, what you'll notice for each corresponding set is that the x and the y values have been swapped. So that would be our rule, and that is in fact a reflection over the line y equals x. So we can add that in as well. Reflection over y equals x. So that proves that L, M, J, K is congruent to Q, R, N, P. So again, as long as you can show that one maps onto the other with some sort of rigid motion, you can prove that they're congruent. Let's look at this next one. So comparing these two shapes, I can see that their size is clearly different. So there's no transfer or translation that would map one onto the other. There's no rotation or reflection. So we can say that NLM is not congruent to EFD because no rigid motion maps one onto the other. Now, of course, another way that we could prove that these two figures are not congruent is by actually finding the length of this line segment and the length of this line segment and showing that they're different. However, the whole purpose of this lesson is to use rigid motion to prove whether something is congruent or not. Okay, so now we're going to try a few where we are told that the figures are congruent. So we have a congruent statement here. And our job is to find a sequence of rigid motions that maps one onto the other. So we're helping them prove that what they say is correct. And we're going to give that coordinate notation for the transformations we use. So let's start by comparing these two shapes. So one thing that I find to be helpful is kind of comparing two parts that you know correspond. So I can see that JK corresponds with this WX. So I notice here it's on the bottom of my figure, here it's on the top. So I'm thinking, oh, maybe a way that I can fix that is by reflecting over the x-axis. So let's see what that would look like if I do my reflection. So J would reflect, K reflects here, L, and M. So now I have something that looks like this. So this is close. At least it looks like it has the right orientation now, but we're not quite there yet. So let's see if there's another rigid motion that we can do to move this to here, this to here. So I notice from here, if I go left 2, down 1, it's the same left 2, down 1, left 2, down 1, left 2, down 1. So then I can translate left 2 and then translate down 1. So then that would map this figure onto this figure. So now we need to write these as a coordinate notation. So we start with x, y. The way we describe reflecting over the x-axis is we're going to make the y's opposite. And then that brings us to here. And the way we get from here to here, well, the way you move left is subtracting from x, and the way you move down is subtracting from y. So this is our sequence of rigid motion that proves that these two figures are congruent. Okay, now let's look over here. So again, we're going to try to make this sequence of rigid motion, and let's look for parts that look like they should match. So I know like this CB looks like it should match with RQ. So if you kind of look where it is on this figure, it's at the bottom right, and on this figure it's at the bottom left. So I'm wondering, how can I make this go to this side of my figure? And we can try doing a reflection over the y-axis. So let's see what that would look like. So my B value would reflect, my C value reflects, my D value reflects to right here, my E value reflects over to here, and my A value reflects here. Okay, so now we have something that looks like it's at least orientated in the right way, but now I can see that we are going to translate our figure down to make it map onto itself. So let's count how many units down. Notice that we are counting by 2 on this XY axis, so 2, 4, 6, 8, 10. So then we're going to translate down 10, and that would map this figure onto this figure. So let's make a coordinate notation for this. So the first one was a reflection over the x-axis, and we do that by making, over the y-axis, which we do by making x opposite. And then once we're here, we want to go down 10. So you go down 10 by subtracting 10 from y. And then we are done. Okay, the last thing we're going to talk about is how to determine if angles and segments are congruent. So congruent angles have the same measure, and congruent segments are segments that have the same length. So we're going to see if we can show that these segments and angles are congruent using rigid motion. Now, of course, I could show that these are congruent by actually finding the lengths and comparing them, but we would like to try instead using rigid motion. So I'm looking at these and I'm wondering, I wonder if GH is congruent to EF. So let's try to make this figure map onto this figure. So the first thing I see is that I'm going to need to reflect it going in this direction. So let's say we'll reflect it horizontally. So it would look actually something like this. So again, I'm starting with GH, and then I'm reflecting it horizontally. And then I can see, okay, at least it looks like it's going in the same general direction. Let's see if we can do a translation now. So from H to E, that would be down 1, 2, 3, 4, 5, and right 2. And this would be down 1, 2, 3, 4, 5, right 2. And then we would map it onto this other segment, proving that they are congruent. So we can say that GH is congruent to EF, and we can say because, and then we can list the transformations we use. So first we did a horizontal reflection, and then we translated, and we went left 2, down 6. Okay, so since we showed that we could make GH map onto EF using rigid motion, that proves that they are congruent. Now here, if you look at, maybe you thought maybe GH looks congruent to DC. Here's a reflection. If I shift this up 1 and I shift this up 1, I get something that looks like this. Oops. I get something that looks like this. So you can see that they don't quite match. So we can say, okay, DC is not congruent to GH. And then if you compare GH and AB, to get from H to B, we would go down 3, bring you here, but then to go, if you bring G down 3, you get this. So it doesn't match with AB. So we can also say GH is not congruent to AB. So we've checked to see if there is rigid motion that works, but in this case, there is not. Now let's see if we can look at the angles to see if any of these two are in fact congruent. So let's start by comparing maybe A and C. So let's say I do some sort of translation of angle C. Let's say I move it up. So I can see that I would have to move it up 1, 2, 3, 4, 5, 6. So I'd say up 6. And then to the left 1/2. So let's see if that would work for my other points. So let's go from here. 1, 2, 3, 4, 5, 6, and then left 1/2. That brings me to here. And then the last one, 1, 2, 3, 4, 5, 6, left 1/2 brings me here. So if I connect these dots, I get an angle that looks like this. So while one of my sides matches up, this one does not. So we can say that angle A is not congruent to angle C because we tried to use rigid motion, but they didn't line up. Well, now let's see maybe if angle C is congruent to angle B. So the first thing that I might try to do is I might try to reflect it, maybe horizontally. So imagine I reflect it over this line. So this point stays here. My vertex will move over to here, and this point reflects to here. So this is where I'm at now. And then we can see if we can translate one onto the other. So I go 1, 2, 3.5, and then up 1, 2.5. So let's see if that would work for my other one. So that brings me here. So again, what we're testing is if we move it 1, 2, 3.5 to the left, and then up 2.5. So let's try moving this one. 1, 2, 3.5, up 1, 2.5. And it actually falls on this line right here. And now let's try from right here. So let's go 1, 2, 3.5, and then up 1, 2.5. And that brings us right here. So if you connect through your dots, you'll see that it does make the exact same angle. So here, we can say that angle C is congruent to angle B, and then we have to state our reasoning. So we can say because the first thing we did was a horizontal reflection, and then we did a translation left 3.5, up 2.5. So I do want to point out that for angles, the length of the sides don't need to be the same. It's really just that measure. So I understand that this angle, these sides are shorter than these sides, but it doesn't matter how long they are. The arrow implies that it would go on forever. So as long as the lines fall on top of each other, we can say that they are congruent. So again, just a quick reminder, your goal for tonight is to show that objects or figures are congruent using rigid motion. All right, that is all for today's lesson. Thank you for watching.